Hello students and welcome to a new lecture. This chapter will be about intermolecular forces. So when we look at the kinetic molecular theory of all states, we figure out that in gases there is a total disorder, there is much empty space between the particles and they have the freedom to move. Now if we cool them down or increase the pressure on them, then they will condense to liquid where still there is disorder for the particles and they move relative close to each other and they are free to move, but it's not like a movement like gas particles. And if I keep cooling furthermore, then I get to solid when there is a rigid order between the particles and they are fixed in positions. They are so close to each other. Now, intermolecular forces are those forces that exist between different molecules. So in this graph here or in this picture, you want to look at the pink lines, and those are the forces between molecules and not within a molecule. The purple lines are the ones are between molecules, or between the atoms within the molecule, within the molecule. However, the pink one are the ones that we are studying, which is what hold molecules or different entities close to each other. For molecular compound, the intermolecular forces, they are what we call attractive forces between molecules, which means they attract each other. They determine the boiling point, melting point, state at room temperature, etc. How strong they attract each other will affect would they boil easily, would they melt easily, would they exist as solid? And if they are strongly attracted to each other, the answer is yes, because they're going to be close to each other. Or if that interaction is very weak, then they are not really feeding each other and they can be, for example, a gas. Intramolecular forces, on the other hand, is the atoms, what hold the atoms together within a molecule, like covalent bonds. For ionic compounds, please take a note of this information. The intermolecular forces are the ionic bonds, which is also the intra. So for ionic compound, inter and intra are the same and are what we call the ionic bonds. Let me show you how in a small little picture. So this is sodium chloride, right? It's a cation next to an anion. And if I have another sodium chloride, it will rearrange itself in that way. So now if I am looking at the formula and trying to see what attract them to each other, then we're going to say, oh, okay, it is the positive charge next to a negative charge, then this is ionic attraction. That's an ionic bond, a cation next to an anion. But isn't that also what attracts them within the same formula bond, like the anion is attracted by electrostatic attraction to the cation? So in ionic compounds and ionic compounds only, the inter and intra are the same and they are the ion-ion forces, or what we call ionic bond. Now, it takes 41 kilojoule to vaporize 1 mole of water because I'm trying to break the inter, the forces, the attraction between molecules. If I vaporize water, it means I'm going to separate them from each other so they become gases. However, it takes 930 kilojoule to break the covalent bond in a mole of water because I'm trying to break intra. Conclusion: generally speaking, intermolecular forces are much weaker than intra, and they should be, right? Now, what are the things that we can look at so we can judge how strong intermolecular forces are? Boiling point. If the boiling point is high, I have a high energy need to separate them from each other, then that means that the strength of the intermolecular force is really high, right? Strong intermolecular forces. Melting point, heat of vaporization, heat of fusion, heat of sublimation. All of the following are measures of how strong your intermolecular force is. There are different types of intermolecular forces. The first one is what we call dipole-dipole forces. Those are attractive forces between polar molecules. Remember, a polar molecule has a dipole moment, right? So look at the following picture. Any polar molecule, one end is red, rich in electrons, the other end is blue, poor in electron. So when a polar molecule is going to sit next to a polar molecule, it's not going to sit like randomly. It will be done in like the positive end is close to the negative end, and the negative end close to a positive end, and so on. That kind of attraction is what I call dipole. So it only exists in polar molecules. You have to have polar molecules. The more polar the molecule, the stronger the dipole. The next type of intermolecular force we're looking at is what we call ion dipole force. These are attractive forces between an ion and a polar molecule. So, for example, if I dissolve sodium chloride in water, then the ions will dissociate and sodium cation will be surrounded by water molecule. There will be attraction between the cation and the water molecules and the anion and the water molecules. And it will be done in a way that the cation will be surrounded by the negative end of the polar molecule and the anion by the positive end. Those dashes, those red dashes, is what I call ion dipole because they are attractive forces between the ions in the center and the dipoles of the surrounding polar molecules. Now, the stronger the charge, the higher the charge, the stronger the interaction between the ion and the polar molecules. So it's not a coincidence that sodium cation with water is weaker interaction than magnesium cation with water because magnesium has double the charge. Next intermolecular force is what we call induced dipole, which are separation of charges induced in a nonpolar substance by proximity of an ion or polar molecule. So here is a molecule, and if we put it close to a cation or a polar molecule, so what's going to happen, there will be an ion-induced dipole. And what does that mean? If you put the molecule next to a cation, right, then the electrons in this molecule will like to come to that side that's close to the cation, which will give me an ion-induced dipole. So this dipole got to be induced by the ion. Now also, if I put a nonpolar molecule in close proximity to a polar molecule, so this is here, guys, this is a nonpolar molecule. So if you put it close to a polar molecule, which has a dipole, right, that's normally what a polar molecule has, then the electrons in the nonpolar molecule will come to the end that's closer to the positive portion of that polar molecule, and therefore that also gives me what we call an induced dipole interaction. Now, remember, there are constant motion of electrons within molecule that can create instantaneous dipoles. So here is the helium atom. It has 2 electrons. Those 2 electrons rotate and they have different spins, meaning if one is rotating clockwise, the other one is rotating counterclockwise. Now, at one point in their rotation, they will end up being at one side of, if one of them is rotating this way, the other one is rotating this way, at one point, one end of the atom has more electrons than the other end. So this is a dipole that's created. It's not permanent though. That's the difference. In a polar molecules, those dipoles are permanent. This is not permanent. This is temporarily, right? And what would that do? That instantaneous dipole can induce a polarity in a neighbor helium atom. So look here at this picture. This one here, the fact that at one point there were more electrons here made that portion has a partial positive. So the next atom will feel that this is a partial positive, so the 2 electrons are going to come to be next to it. And now that creates a partial positive on this one, so these 2 electrons are going to come to it, and that creates a partial positive, and so on. Now the thing is, Those are not permanent because they're going to keep moving, right? So each one of them will be moving in the opposite direction, and that will break and reform and break and reform and break and so on. That will exist anytime you have electrons. Anything that has electron will have that, what we call London dispersion forces. So these are attractive forces that arise as a result of instantaneous dipoles in atoms or molecules. All intermolecular interactions involve London dispersion forces. Anytime we have electrons, we do have London dispersion forces. Now, the dispersion force's strength will depend on something we call polarizability, which how easily the electrons distribution can be distorted. The more it can be distorted, the stronger the polarizability is, the stronger the London dispersion forces. So polarizability increases with more electrons. The more electrons you have, the more chances that you will have random distribution of electrons, which means one side will have more negative charge than the other. The larger the size of the atom of the molecule, the more polarizability they can have. So more polarizable, it means larger dispersion forces. Therefore, how can I increase number of electrons? Number of electrons naturally increase with number of protons, which naturally increase with the molar mass. So the higher the molar mass, the stronger the dispersion forces. You can look at the following table here, and you will see that you have compounds. All of them are nonpolar. Methane, tetrafluoromethane, tetrachloromethane, tetrabromomethane, tetraiodomethane, all of them are nonpolar. So, because they are all nonpolar, the only intermolecular force existing is dispersion. However, there is a huge difference in melting point, and it does increase as the molar mass increase. If I ask you to explain why this melting point increasing significantly here in comparison to methane, it's because with the increasing the molar mass, London dispersion forces did increase significantly, which cause an increase of melting point. Remember how melting point is a measure of how strong intermolecular force is. Okay. Then there is a special type of dipole-dipole that we call hydrogen bond. Hydrogen bond is not a new intermolecular force, it's just a special dipole-dipole interaction, and it will exist only when I have a hydrogen atom in a polar bond. So I have to have a hydrogen, and this hydrogen has to be bonded to either nitrogen, oxygen, or a fluorine. And it will have a hydrogen bond with another nitrogen, oxygen, or a fluorine. I call them the FUN, F-O-N, okay, FUN. So if I have a hydrogen, here is the condition. The hydrogen has to be bonded to one of the three atoms, which it is, and the dots is what I call hydrogen bonding. And the hydrogen bonding does happen to another one of those three atoms, right? So the hydrogen has to be bonded to one of the three, and it will hydrogen bond to one of the three. So now let's look at more examples here. Why do I have to have the hydrogen bonded to one of those three atoms? What do these three atoms have in common? Two things. They are very electronegative and they are very small. What does that mean to me? Very electronegative, it means that this bond is very polar, all of them, which means I have a large partial and a large negative, a large partial positive and a large partial negative, and so on. And the size is so small, which means that the partial negative is intense and condensed in a smaller size. It's not diluted over a big volume. That's why it causes a lot of attraction and a special dipole-dipole bond. Here are examples. Look at the red dots are hydrogen bonding. This hydrogen is bonded to one of the three atoms, and it is hydrogen bond to one of the three. This one bonded to one of the three atoms, and it's hydrogen bonding to one of the three. Bonded to one of the three atoms, and it's hydrogen bond to one of the three, and so on. And by the way, intermolecular forces do not need to take a place between identical molecules, meaning it doesn't have to be water hydrogen bond to water or ammonia hydrogen bond to ammonia. Water can hydrogen bond to ammonia, and ammonia can hydrogen bond to hydrogen fluoride, and so on. Here is another picture of the hydrogen bond in water. And again, you can see that the hydrogen is hydrogen bonding to the other atom of the three. Now, let's see why hydrogen bonding is considered a special dipole-dipole. Let's look at the group 4A here. So silicon trihydride and germanium trihydride and tin trihydride, what do they all have in common? All these are nonpolar molecule. So before silicon, who's gonna come here? It will be carbon, methane. And what am I measuring here? I am measuring the boiling point. And what I am realizing that if I need now the question or of this slide, predict where methane should be on the boiling point. If the increasing of the intermolecular force is going this way, because the molar mass is increasing and therefore intermolecular forces, which is London dispersion forces in this case, why? The molecules are nonpolar, that's the only one that exists. Then I should expect CH4 to be here, right? Because the boiling point should increase as I go in that direction. Now, before sulfur here, I have oxygen, so I am talking about water, right? And the molar mass does increase this way, and therefore this is a higher boiling point than this, and this is a higher boiling point than this. So where should I expect water? Since water has a lower molar mass, I probably should expect it to be somewhere here, H2O, right? That's what I expect based on molar mass, but I am not taking into account that when it comes to water, these molecules, by the way, are polar. So the intermolecular force between them, they all have dipole-dipole, all of them, right? So the only difference will be in London dispersion forces, and it will increase with increasing molar mass. Now let's see what reality is. That's my prediction. Now let's see where my reality is. For methane, I was right because it was only London dispersion forces. For water, I was wrong. Look what hydrogen bond, how strong it is, right? It didn't care that I am losing London dispersion forces by molar mass. The fact that it does exist, it increases the boiling point significantly. This is how strong hydrogen bonding is, and that's why we treat it as a special dipole-dipole. Okay? Now, which of the following can form hydrogen bonds among themselves? Let's examine this question together. H2S. Now, H2S, this is the molecule here. And can it form hydrogen bonding with each other? Well, the condition is the hydrogen has to be covalently bonded to one of these three atoms. So the answer is no. Immediately no. No discussion. Benzene. Carbon and hydrogen, no way, right? Because carbon and hydrogen together are always going to make nonpolar bonds, right? There is no polarization, which means the only thing that can possibly exist is London dispersion forces. Does not exist, okay? Methanol. Now, methanol has the following Lewis structure. So, do I have a hydrogen bonded to one of the funds? The answer is yes. This is the only hydrogen in the molecule that can hydrogen bond, and it will hydrogen bond this way. So let me draw it down for you. So if this is the other methanol, then the hydrogen bond will exist between the hydrogen bonded to the oxygen and the oxygen. Okay, how about dimethyl ether? Can it hydrogen bond to dimethyl ether? The answer is no, because the hydrogens here are bonded to carbon, not one to the three atoms. However, can this ether hydrogen bond to water? The answer is yes. How? Because this hydrogen in water is bonded to one of the three, and it can hydrogen bond to one of the three atoms, right? So this is really takes a practice and takes looking at many molecules, so you actually can make that distinguish. Which of the following can form hydrogen bond with water? We just talked about ether, so we said ether. Although those hydrogens on carbon cannot hydrogen bond, however, water can hydrogen bond. Okay. Methane? No way. Why? No hydrogen is attached to one of the four, and there is no way this hydrogen can hydrogen bond. Fluoride anion. The answer is yes. If I have a water, a hydrogen bonded to one of the three atoms can hydrogen bond to fluoride. Acetic acid, so which has the following actually this is for formaldehyde, so this is formic acid. And can it hydrogen bond to water? The answer, this hydrogen can. This one no, because it's attached or bonded to carbon. So yes, I can hydrogen bond this one to water. And sodium cation, can it hydrogen bond to water? No, because this is not one of the three atoms. Okay. Now, here is how you decide what intermolecular forces you're looking at. The first question you ask yourself, am I looking at a molecular or an ionic compound? If it's ionic, which made of metals or nonmetals or polyatomic ions, then what does exist is ionic bond and dispersion forces. Remember, dispersion forces will be everywhere, right? Remember, ionic bonds, inter and intra are the same, which is the ion-ion or the ionic bonds. If the molecule is molecular, then your next question, is it polar? If the answer, no, it's non-polar, then the only thing that exists is dispersion forces. If it's polar, then does it contain the nitrogen, hydrogen, oxygen, hydrogen, fluorine, hydrogen? If the answer is yes, then it does have hydrogen bonding, dipole-dipole, and dispersion. If the answer is no, then it only has dipole-dipole and dispersion. What type of intermolecular forces exist in each of the following species? Let's see. This is a polar molecule, but it doesn't have hydrogen attached to one of the three atoms. So what will exist here is dipole-dipole and London dispersion forces. This is a nonpolar molecule. The only thing that exists is dispersion forces. This is a polar molecule, and I will know that once I draw the Lewis structure. And therefore, this is dipole-dipole and dispersion forces. This is a polar molecule, and it does have a hydrogen bonded to one of the three. So this one has a hydrogen bonding, dipole-dipole, and dispersion forces. Lithium chloride, this is an ionic compound, so it does have an ion, and dispersion forces. This is a cation with a polar molecule, so this one has ion, dipole-dipole, ion-dipole, and of course there is always dispersion forces anytime you have electrons. Now, when it comes to that spectrum, the molecules that are nonpolar are at the end of this spectrum, and it does have London dispersion forces. The other end of the spectrum of polarity is ionic compound, and they have ion-ion interaction. In the middle are polar compounds. If it's polar without the hydrogen with the fun atoms, then it's dipole-dipole interaction. If it has one of those, then it's hydrogen bonding. Hydrogen bonding is definitely stronger than just dipole. Okay, I hope you had fun with this lecture, and I will see you in the next one.